Hello everyone, welcome to this video. In this video, we'll be continuing with the properties of subgroups under homomorphism. So previously we have studied about the 5 properties. Now let's move on to the 6th property. We have assumed that phi is a homomorphism from the group G to the group G bar and H is some subgroup of this group G. Then if the order of this subgroup H is given to be H, then we say whatever is the image which is formed by phi of this H, right, which is phi of H, that its order divides the order of H, correct? This is the result. So now let's prove this result. We know phi from G to G, phi of G, that is a homomorphism. So what we do, we take a restriction phi of H of this mapping phi. So that means our domain, instead of taking the whole group G, we now take a portion of it which is H, correct? Now, and we apply this mapping phi onto this H and call that restriction to be phi of H. So here we have G bar, right? So here it would lead to some shorter set here, right? Smaller set here, which is what? Which would be your phi of H. Correct. So we now define phi of H to be a restriction of this mapping phi. Hence we are saying this phi of H is also a homomorphism. Why it is a homomorphism? Basically because phi was homomorphism and we had operation preserving property for all the elements present here. So in short, we would have the operation preserving property for H as well. Correct. Hence this is a homomorphism. And now we also assume that the kernel of this mapping phi of H has elements T, right? So its order is T. We are assuming this thing. Now if you remember the definition of kernel of some mapping, it is what? It is phi H of E bar, right? It is phi H of E bar. Why? Because if you take some element G here, then it is G here, right? But now we are taking E, so here it is E dash. So basically E dash with kernel phi is what? It is just kernel phi H, correct? So this is this mapping phi H of E dash and it consists of all those elements X belongs to capital H such that phi H of X is equal to E dash. Right, this is the definition that you already know. Now we are assuming the kernel of phi H to be T, right? Its order is equal to T. Hence, the order of this phi H of E dash is also T, correct? This is what we have. Now, what does it mean? It means that for every for this to mean that for every this mapping phi of H is a T to 1 mapping, which means that for every element in phi of H, we there are exactly T elements in H. For example, you have this phi of H and this as your subgroup H, correct? And we have the mapping phi. So that means for every element here in phi of H, we have exactly T pre-images of this in H, right? And how many such, suppose here we have M such elements. So here we would have M into T such elements, correct? That is what we meant by a T to 1 mapping. Hence, H contains T times the number of elements present in phi of H. And this could be written as the order of H is equals to T, the order of phi of H. Hence, the order of phi of H divides the order of H. And this is what we wanted to prove here for this particular property, right? So I hope you understood this property well. Well, that is it for this video. Thank you for watching.